Earlier in this chapter, we have learned that a conductor or a wire with a current flow will produce a magnetic field around it. This magnetic field will exert a force towards a permanent U-shaped magnet near to the conductor. So how does this conductor move? According to Newton's third law, every action force there will be a reaction force. The same amount of force will be exerted on the conductor from the permanent magnet causing the conductor to move. Every conductor with a current flow, when it is placed in a uniform magnetic field, it will experience a force that causes the conductor to move. In this case, the conductor will move downward because the direction of force is downward. Let's look at the situation here. Both conductors with a current flow will bend towards each other because they experience an attractive force due to the magnetic field produced by each of the conductor. The magnetic field produced is not from the permanent magnet like the previous example, but produced from the neighboring conductor. Remember from the animation in the previous video, a charge will deflect in circular motion when it is moving in uniform magnetic field. Since there are moving charges in this conductor due to the current flow, the force acting on these charges is the same force that caused the conductor to move. Hence, we can apply the right-hand rule to determine the direction of force. The thumb always shows the direction of force, the four fingers follow the direction of moving charges, and the palm facing towards the direction of magnetic field. So the magnetic field in this case is into the page, like this arrow here, because the direction of magnetic field is from north towards the south. If you can't recall what is the right-hand rule, please refer to the previous video. So let's try this out. The current in the conductor is to the left, follows the direction of positive charges. So the four fingers must pointing to the left. Magnetic field is out of the page, so the palm must facing outward towards you. You will see the thumb will point upwards, showing the direction of force, and the conductor will move up. The formula to calculate the magnitude of magnetic force comes from the formula of F equals to QVB sine theta, where F is the force acted on the positive charges. So we substitute the formula of velocity equals to distance over time, and the distance is equals to the length of the conductor since the charges are moving at a distance L within a time t, and we have a formula that relates charge and also current, where current is the flow of charge, Q equals to IT. Therefore, the formula will become F equals to ILB sine theta. The actual formula is written as F equals to current and the cross product between length of a conductor and magnetic field. Since length and magnetic field is a vector quantity, we can write the formula in terms of magnitude with sine theta at the end. So the F is the force acting on a conductor or wire with an SI unit of Newton, and the L is the length of a conductor in meter. I is the current through conductor, current flow through the conductor in ampere, and B is the magnetic field strength in Tesla, and the last one is theta, is the angle between the conductor and magnetic field. So to determine this angle, we can simply look at the angle between the current flow and the magnetic field. Let's check out the angle between current and magnetic field for this case. The four fingers follows the direction of current in the wire. So we can assume the current is into the page for this case. And then the palm is facing to the right because the magnetic field B is from north towards south. Okay, so that is B. So we can see now the angle between current and B, I and B is now 90 degree. So by using the formula of F equals to ILB sine theta, our theta now is 90 degree angle between the current and also magnetic field. Therefore, sine 90 will give you 1. And by looking at the direction of thumb is pointing downward, so it shows that direction of magnetic force. Hence, the conductor will move downwards. So I think that's the end of the video. Hope everyone enjoy learning this topic and thank you for watching.